Hey everyone, welcome back, and let's write some more neat code today. Let's solve number of good leaf node pairs. Leaf nodes pairs? I feel like that is kind of incorrect, but anyways. The reason I'm on this page, by the way, is I wanted to show you guys something I thought was kind of funny. I solved this problem 4 years ago, and can you believe this? I swear it's not what it looks like, and I'm honestly not sure why I was using Java anyway. I would never betray Python, but anyways, let's get into the problem. We're given the root of a binary tree and a second parameter, which is the distance. Now, it's kind of similar to the last couple of problems we've solved in the sense that the lowest common ancestor is going to be relevant here, because if you look at it, what they're asking for us is, given some leaf nodes, in this tree, there's only 2 leaf nodes. This is a leaf node and this is a leaf node. By the way, a leaf node is just a node that doesn't have any children. They ask us for the shortest path between 2 leaf nodes, and it's pretty straightforward. It usually just runs through the lowest common ancestor. So in this node, it's going to be a distance of 2 on this side, and on that side, it's going to be a distance of 1. So you add those 2 up, you get a distance of 3. Now, the threshold that they give us is all the distances have to be less than or equal to this threshold. And of course, this is true in this case. So we found one pair that is valid. So we want all these pairs and we want to count them. We don't really need to identify what they are, just count them. And in this problem, we only have a single one in this example, so we would return 1. That's the idea of the problem. And believe it or not, what I kind of showed you here is a lot of the intuition to solve the problem. There actually is 2 solutions though. It's kind of debatable, honestly, which one of these is more efficient. There's going to be the tree solution, which at first seems like it's an n-cubed solution. I actually made the mistake of thinking it's n-cubed. Technically, this is a valid upper bound, but when you get more precise, we can show that the real complexity of that solution would actually be something like this: n times d squared, where d is the second parameter. By the way, n would just be the number of nodes in the entire tree. So this would be the time complexity of the solution I'm going to show you. Well, the first solution. Now, the second solution is actually an n squared solution. So it's kind of not clear which one of these is technically more efficient. Consider this example tree where the distance is 3. How would you do it? Just pen and paper, how would you do it? Well, we mainly care about the leaf nodes, right? So of course we want to run some kind of traversal and find all the leaf nodes. Now, from the root node, that's probably the first question you would ask is, what are the leaf nodes on the left side? Like, how many are there? In this example, there are 2 leaf nodes. What's the distance it would take for this guy to reach this leaf node? About 2. Same thing with this one, a distance of 2. It didn't have to be that way. Imagine this one had a child, 8. Then the leaf node on this side could have been 3. So we could have leaf nodes on one side of differing lengths, but there could be multiple of them. There could be 1, or there could even be 0. Imagine there's nothing on this side. Take that into account. So this parent needs to know that. Now, of course, that should be stored in the form of a list. So let's say we have 2 and 3, and this is, or well, for this example, it's 2 and 2. So on the left side. And obviously it's a symmetrical tree. So the right side is probably going to do the same thing. So I'll just put it over here. There's 2 leaf nodes from the perspective of this guy, and the length to reach each of them is 2. If you had that information and you wanted to know the shortest paths that run through this node, what are the lengths of all of them, and are they less than the distance that we're given? Well, it becomes a pretty simple problem, isn't it? Like, we just want to go through every pair. Just to make it really, really clear, let's say we have 2 on this side and 2 on this side. We just want every pair of them. This is one pair, this is another pair. This is one pair, and this is another pair. There are 4 pairs. How do you get pairs with 2 lists? Well, it's called nested for loops. Isn't that right? So that's a very easy problem to solve. But what exactly are we solving? Well, we get the distance of each pair. So like from the perspective of the root, it's like 2 in every single case this time. So it's pretty simple. So every single pair would take the distance, like from here, if I want this one, it's a distance of 2. From this side, I get this one, it's a distance of 2. So I want to know, is this pair of leaf nodes valid? Well, you take the distances and add them up. 4 is definitely not less than or equal to 3. It's not valid. What do? we don't count it. So that's all it is. It's a game of counting these types of pairs. This might have seemed very simple to you. The only hard part I think about this problem is that it kind of needs to be solved bottom up. We're going to ask that question from the root eventually, but it's not the first question that we're going to ask. We're actually going to run recursively DFS on the left subtree, same with the right subtree, and we're going to ask the question here first. We're going to say, what are all the paths running through this node from leaf nodes on the left side and on the right side? That begs the question, what's the base case going to be? Well, from here, we're always thinking in terms of returning a list to the parent, right? That's what the result is going to be, a list. But the base case is going to be a leaf node. It's not going to be null. I mean, I guess null would probably just return an empty list. We can handle that, I guess, depending on if we're given an empty root of a binary tree. But the leaf node case is what we're really concerned with, and we're going to return a list. You might think we're returning 0 at first. It technically could work, but I think it's better to return an array of 1 because that tells the parent that it needs to travel a distance of 1 to reach this leaf node. And that's correct. That's what we actually want. If we get the same thing on the right side, we'll get a list of just the value 1. So we see that we have 1 leaf node on the left side, we have 1 leaf node on the right side, and we do the same thing, the nested for loops I was talking about. And so we can only form 1 pair like this that runs through here. The distance of it is going to be 2. That's less than 3. So we did find 1 valid pair here. Obviously, it's symmetrical. We'll probably do the same thing on the right side, found another valid pair here. But now, what would we return up to the parent? Think about it for a second. The parent needs to know what are all the leaf nodes on the left side and what's the distance it would take to reach them. Well, it's not too bad. We saw that this is a distance of 1, this is a distance of 1, and it didn't have to be that way. Let me just show you kind of a counterexample. Maybe there was another node over here, and maybe this distance was 2. Well, either way, the distance from the root or the parent from here is just going to be a +1, obviously, right? It's just 1 more edge added to this. So this would now be a 2 from the perspective of this guy. This would be a 3 from the perspective of this guy. So what I'm saying is the base case was pretty easy. Leaf node just return a list that looks like this. But the non-base case is going to return something different. It's going to take both of these lists, combine them, and get this. And not only that, take the values, every single value, and add 1 to it. Get 2 and 2. If the original list was 1 and 2, then we would have added 1 to each of these, and we would have gotten something like 2 and 3. Either way, just add 1 to every element and then return it. So that's pretty much the entire problem. Now, technically, the solution I've shown you so far is n cubed, because the number of pairs that could be returned from each left and right subtree could be n, or roughly n, not literally n, but proportional to n. So going through nested loops to get those is going to be n cubed. But there actually is an optimization that we can make to get this down to nd squared. I'm going to first code up the n cubed solution and then do the optimization to maybe give you a chance to try to figure it out by yourself. I'll give you a second hint, by the way, in a bit. It's actually a 1-word hint that probably will give it away, which is why I'm saving it for later. So the first thing I want to mention is the way we're going to be counting the pairs. Our DFS is not going to return the count. It's going to take a parameter, which is the current node, but it's not going to be returning the number of pairs. So we're going to be doing that independently. Like as we're going to be independently updating this global variable. Well, it's more of a member variable. It's self.pairs. I could, just declare it and then make it non-local down here, but I think this is probably the solution that's more easy to translate into other languages. So if you're using Java or something, this is the same as having like a member variable that's declared like up there. So I'll kind of leave it there to make it more consistent. In this DFS itself, it's not going to be too bad. Remember the main base cases. I will cover this one where we get to a null node, even though I'm pretty sure we're not going to be given an empty tree, but that would be doing something like this. Otherwise, we have a leaf node, which is also a base case, if not a node.left and not node.right. Then we're going to return an array that looks like this. Next is, of course, the recursive case. So I'm going to have a couple variables, left distance, which is what's going to be returned from DFS node.left. Same thing for the right side. This is pretty simple. We just assume that it works right now. We're just assuming that we're going to get those distances from each respective subtree. But we will have to code up the logic for that, which I guess I'll do now. Before even the nested loops, this is what we're going to do. Let's combine these two lists. In Python, the easiest way to actually do it is something like this. Let's do all distances, left distance plus right distance. This will pretty much concatenate the two lists together to create a new one. And then what we want to return is actually not this new list, but it's similar. We're going to add 1 to every element in this list, which again is pretty easy to do in Python using something called list comprehension. So I'm going to say for distance in this array, then I'm going to say d plus 1. So this is creating a new list by just adding one element to each of these. Okay, now for the nested loops part. This is the part where we're actually doing the counting. I'm going to go through every pair, d1 in left distance and d2 in right distance. And if the sum of these two distances is less than or equal, make sure to include the equal sign, is less than or equal to the parameter distance that we're given, then we will increment the number of pairs, which we declared all the way up there. So self.pairs plus 1. So that's pretty much it for the recursive function. The only thing now to do is return self.pairs, but I always forget this part, so don't be like me. Make sure to actually call your recursive function. So do this, dfs root. I'll run this. Okay, that's kind of embarrassing. We can't actually do this in Python. That needs to either go in the constructor or here, because if you see in Python, self is actually not like a keyword. Well, by itself, it's not. It actually gets passed like into the context of a function. Minor change. And you can see it works. It's relatively efficient, but there actually is an optimization we can make. And I'll give you the second hint. It has to do with counting. We here have a bunch of distances, but if we had like 3 leaf nodes on the left side or multiple leaf nodes on this side, and the distance of each of them is like 2, we can count them together. Another thing would be if we had some distances in this side that already exceed the distance here, why would we even keep track of them? There's really no reason for us to do that. So what we can do is something like this. The idea is that we can use either an array or a hash map. In that hash map, the key will be the distance itself, and the value that that maps to will be the number of nodes with that distance. In addition to that, we won't add any distances to this that exceed this distance. So that will limit the length of this hash map. We could have also done the same thing with an array. I just prefer using hash maps whenever I can. But that alone isn't enough. Suppose on the left side we had a distance of 3 and we had 2 nodes with that distance. And suppose on the right side we have a distance of 1 and we had 2 nodes with that distance. To count the total number of pairs, we would first get the distance here and get the distance here, add them together. It's 4. And suppose 4 was less than our threshold. Then what would we do? We would take the number of nodes here and the number of nodes here and multiply them, not add them. I guess in this example, it would be the same, but suppose I change this to a 1. We wouldn't add 1 node and 2 nodes because if these are on the left side and these are on the right side, we can't create 3 pairs from them. We have to multiply this by this. We can only create 2 pairs. This node would be paired up with either of those. So that's the idea. That's how I'm going to code up the rest of this. First, since we're using a dictionary, here I'm going to just return a default dict that happens to be empty, where the value is going to be an integer. Here, I'm going to do kind of the same thing. I'm going to create one, I guess. I'll call it count. And then here, just to make this very, very clear, what we're saying is count. The distance of this is now going to be 1, and we found 1 leaf node, so we're going to do this. And then we're going to return that. Down here is going to be a little bit more tricky. Well, this part isn't going to be too bad. These are the keys. They stay the same because remember the key of this map is going to be the distance. So distance 1, distance 2, adding them together. If it's less, then we add to pairs. But we don't add 1. We will add the count of left distance with this as the key multiplied by the count in right distance with this as the key. So this is updating that. Now for the result, this is going to be kind of the tricky part, because we can't just concatenate these two hash maps together because we have to limit the number. So what I'm going to do here is just rewrite this portion. So I'll still create a default dictionary for this. First, I'm going to go through left distance. So I'm going to say for D in left distance, if D plus 1, remember, we're always going to increment that distance by 1. So we want to check not just that D is less than the threshold, but D plus 1 is less than or equal, I guess, to the threshold. And if it is, we can go ahead and add it to all distance. So here with D plus 1 as the key, we will add to that, not just assign it, but add to that the count. So left distance at D plus 1. I guess for the first cycle, we probably could have just assigned it. But when we copy and paste this and do the same thing for the right distance like this, so I'm just going to kind of rename all these, right dist, and copy and paste it there. And we're good. Here, we're definitely want to increment here. And then we are good to return all dist. So this is the final code. I think it might actually be technically shorter if instead of using a default dictionary, you used an array and just limited the size of the array to like distance plus 1 or something like that. So you can do it if you prefer that way, but this is fully optimized. Let's run it. Okay, I had a very, very subtle bug and I apologize. So when we're adding or, assigning this, we have this key D, which maps to the count in this map. When we assign it to all distance, though, we want to do D plus 1, of course. But from the right side, there's no reason for us to increment here. There's no reason for us to have the plus 1 there. That's my bad. And I apologize if it was confusing. But now you can see it works, and it's definitely the most optimal. So I want to briefly run through the second solution. Conceptually, it's actually pretty simple. It just happens to be a lot of code. Running through it, consider like the graph over here. So just to zoom it in. Imagine this was not a tree and it instead was just a general graph. How would you solve the problem? Well, remember, we're looking for the shortest path between one leaf node to another. So from the perspective of 4 over here, the shortest path from it to 5 is going to be 2, all the way to 6 is going to be 4, all the way to 7 is also going to be 4. Obviously, only this one is going to be valid. If it was a general graph, how would you do it? Well, probably a BFS. Breadth first search is generally good for finding shortest paths when the edges don't have a weight. So we can use breadth first search. The only thing would be we'd need to convert this into a graph, and we'd need to identify all of the leaf nodes so that first we could start running a BFS from all of the leaf nodes, and second, we would be able to know when we reached a different leaf node from the start of another one. That algorithm obviously is going to have 2 phases. I'll show them to you now. Phase 1 would be building the graph. You can see the code here isn't super crazy. I have a function which is going to be called given the root of the tree. And if we reach the base case of if not node, we will return. If the left node is non-null, well, then we found an edge. The whole point of building a graph is just getting all of the edges. So if this node has a child, we can say in the adjacency list, this node will append to the list its child. And not only that, but its child will append to its list the parent because these edges are undirected. We do the same thing with the right child. And most importantly, when we reach a leaf node, we add it to our leaf hash set. And we also do recursive call here. I think if we really wanted to, we might be able to shorten this up a bit, but I don't think it's super important. The next phase after calling build graph is going to be running a breadth first search on all of the nodes that are in the leaf set. And we'll have a variable here, a member variable that we will increment within the function. And then down here, I'm actually dividing the result by 2. I'll explain why in just a second, but BFS here, it's just a very standard BFS. So we start at the node that we're given and we keep track of the distance because that's definitely going to be important. So here we start with the node. Initially, it's at a distance of 0, and then we run breadth first search while the queue is non-empty, pop from the queue, get the node and the distance. If it's not the same as the original node, and it is a leaf node, and the distance is below the threshold, then we found a valid pair, increment this. Next, go through all the neighbors of that node, and if the neighbor hasn't been visited, that's important. We don't want to do duplicate work. We don't want to get stuck in an infinite loop or cycle. well. So keep track of visited nodes. And if the neighbor hasn't been visited, go ahead, append it to the queue, add a distance +1, because it's obviously going to be +1 distance further than the current node, and also add it to visit. Why am I dividing by 2? Because think about it. If we run a BFS from every node, we're going to get the path from 4 all the way to 5. We're also going to get the path from 5 all the way to 4. So that's why we're doing it that way. And this solution will work. Now that I look at it, I think there is an optimization. There's no reason for us to add neighbors if their distance +1 exceeds the threshold. So I guess here we could also say and distance +1 is less than or equal to distance. So I'll just add that little optimization there. And now I'll go ahead and run it. Okay, I don't know why I didn't finish typing that word. And there you go. You can see, though, that it's not as efficient, at least in terms of the Leetcode runtime, as the previous solution was. But I hope you understood it. Thanks for watching, and I'll see you soon.